Hello and welcome to Rome's BD71847 webinar. My name is Michael Maurer and I'm acting as Product Marketing Manager for Rome Semiconductor, responsible for power management ICs. As you can see, I have long experience in the semiconductor and high-tech industry, especially in ICs with a high integration level for power rails. During this webinar, I will shortly talk about the challenges for power supply designs and guide you through the BD71847 while starting with a global overview and approaching more and more details on the DC-DC regulators, the bill of material, the buck conversion efficiencies, evaluation test results, the PCB layout, and the requested PCB area. Finally, I will show you how to access the product collaterals on our website and some final words regarding our PMIC family for the NXP i.MX 8M processor family. But let's start with the design challenges and start with the selection of the SoC. Today there are so many processors on the market and it's really hard to select the right one. For sure, there are technical reasons for the selection, but you never know if the performance is sufficient to the rapid changing market requirements. Markets are shifting, new technologies are popping up due to new innovation and technical breakthroughs. And there is man with its everlasting energy to think up new things, but always limiting himself by cultural or other constraints. As mentioned, it is a complex and multi-layer process in selecting the application fitting SoC, where economic requirements also play an important role. While just diving into the requested power design requirements, you can see that the effort can be significant due to the increasing complexity of power rails, supply accuracy, transient responses, and a lot of further parameters which need to be respected. Power supply designers easily have to read documentations in the size of books like Gone with the Wind, collect, analyze, interpret requirements not only for the power supplies but also for the sequencing, handshaking, and furthermore. Here's the good message. Rome has already done this for you. BD71847 is the proven PMIC for your NXP i.MX 8M mini processor family, the full processor family, from the low-end to the high-end derivatives. As all requested power rails are integrated, the sequencing and the handshaking is implemented. This PMIC is solving the major power design issues for you. Let's have a distance view to this PMIC. As mentioned, all power supplies for the SoC are integrated. And it's not just the ones for the processor. It's also for commonly used peripherals like the DDR memory, flash drives, or SD cards. Additional features are included in the PMIC for compact designs at a very low cost bill of material and smallest PCB requirements, even while supporting low cost PCBs. The PMIC offers OTP technology for power attribute modification and best flexibility. Before we get closer to the PMIC, here's a quick look to the target application. You can see a great application variety in the field of consumer electronics, smart home and building control, as well as industrial applications, all supported by the BD71847. Let's come a few steps closer to the PMIC. Modern SoCs have optimized cycle per power ratio, but can request high peak power for short period of times. BD71847 can supply on one side up to 32 watt peak into the system at high conversion efficiency of up to 95% and consumes only 30 microamp in low power mode. The requested area for the PMIC and its externals can be down to approximately 300 square millimeter, as the IC comes in a small 7x7 QFN package. Its power supplies, interface, pin out and sequencing is optimized for the NXP i.MX 8M Mini SoC family. Okay, what's the power supply content? 6 high-efficient, high-frequency switching buck regulators at 2 MHz and 1 at 1.5 MHz with automatic or fixed mode are integrated to achieve best performance. 5 out of the 6 bucks can provide up to 3 amp output current at output voltages between 0.7 volt and 3.3 volt. There are 6 LDOs. 2 are requested as SNVS supplies or RTC supplies, and 2 pairs of higher and lower output voltages supplies are integrated. Those LDOs will generate either 1.8 volt up to 3.3 volt or from 0.9 volt up to 1.8 volt. The power supply generation will be completed by a power supply multiplexer for SD cards. All regulators are fully integrated. No active components are externally necessary. What other than power supplies is integrated in the BD71847? Interfaces to interact with the SoC means handshake lines and I2C interface. There is a power button interface with configurable debouncer and detection times for multiple startup behavior and functions, and a 32 kHz crystal driver including instant on clock supply function. BD71847 also offers multiple protection and supervision functions like under-voltage lockout, over-voltage protection, thermal shutdown, power rail fault detection, and soft startup features to reduce the inrush current. All integrated to ensure proper and safe operation. Here you can see how the PMIC will be connected to the NXP i.MX 8M Mini SoC. All PMIC generated power rails have its clear defined peer-to-peer SoC connection, except buck 5, which supplies multiple processor units like the GPU, the video processing unit, and the processor's DRAM. BD71847 integrates one LDO which is not controlled by the SoC. This LDO4 can be freely used by the user and controlled via software, means the I2C interface. Okay, now we will have a closer look to the buck regulators. I have already mentioned that they are switching with 2 MHz. Okay, one is switching at 1.5 MHz. Such high switching frequency and our buck design will allow to scale down the externals as much as possible. Means the input capacitance is just 10 microfarad. The inductor value is down to 0.47 microhenry and the output capacitor is only 2 times 22 microfarad. For buck 7, this is the buck which generates 1.5 amp output current. The switching regulator requests only one capacitor at 22 microfarad capacitance. The impedance of the switching transistors is optimized for best conversion efficiency. The high side transistor has an impedance of around 100 milliohms and the low side transistor is not just the half. Furthermore, the efficiency is optimized with the buck controller logic, which either automatically selects between the PFM and the PWM mode, or it can be forced to run in PWM mode. Please have a look onto the efficiency graph. The efficiency is very flat for a very wide range of loads. It's almost straight between 1 milliamp and 1 amp, and this at a very, very hard voltage ratio between the input voltage and the output voltage. In this graph, the input voltage, as an example, is at 5 volt and the output voltage is just at 0.8 volt. Furthermore, you can see that even for a very wide range of temperature, in this example, minus 60 up to 125 degrees, the efficiency behaves pretty much the same. Let's have a look to the total bill of material. No, we are not going through this list. The message is that the bill of material includes just 42 components and roughly a handful pull-up and pull-down resistor to power up such NXP SoC. That's all with 13 rails. Here you can see the power requirements on the main rails for the NXP processor based on multiple benchmarks and application tests. I even don't want to go through that list, but I have highlighted the maximum current which was measured on the benchmark tests. You can see that there is sufficient headroom for the BD71847 power supply rails to deal with peak power requirements at all. Let's have a look to the buck conversion efficiency in the use cases. First, the suspend mode, then the idle mode, and last but not least, the run mode. As a summary, very high efficiency can be achieved in all three modes, even with the very hard output to input voltage ratio. The next slide is pretty much the same information for the other two low output voltage bucks in suspend, idle, and run mode. You can see even here that the efficiency performance is perfectly optimized for best thermals and long operational times if your application is battery driven. Here you can see the efficiency graphs for the high voltage bucks. As the current consumption of the use cases is heavily depending on the peripherals connected to such rails, there is no detailed information on this. What's clearly visible is the flat and high conversion efficiency on both rails up to 95%. Okay, another quality benchmark for bug regulators is the transient load response. In this sheet, you can find the test results for droops and overshoots for significant load steps which can occur when peak processing performance is requested. All bug regulators have enough headroom for droops and overshoots and the full temperature range between minus 60 and plus 125 degrees C. As an example, bug 2 with its 0.9 volt output, the droop is just approximately 50% and the overshoot there is around 70% headroom. A further quality attribute is the AC ripple of the bug regulator. The measurement was done for low output current. The bug here is in PFM mode, as well as maximum output current when the bug is in PWM mode. You can see that the AC ripple for all 3 amp bucks is in the range of around 10 mV for PWM mode and around 22 mV in PFM mode. This is very outstanding test result. Bug 7 has a slightly higher AC ripple in PWM mode, but still far away from the ripple limits. Here the startup and shutdown times are listed. Tests were done on no load and maximum load. The test results are fully within the limits and the expectation. It is clear that a highly loaded buck regulator, when it switches off, has a significant lower shutdown time versus the buck has no load. Let's continue with the LDOs and have a look to the line regulation. You can see that all regulators are within less than 1% tolerance of the line regulation for the full temperature range of -62 plus 125 degrees C. Next parameter we have measured is the transient load response for the buck for the LDOs from 1 milliamp to its maximum defined output current. The droops and overshoots are within the limits over the full temperature range. This ends the power supply section. Today's modern SoC requests clearly defined power up and power down sequences. Such power sequences are requested to avoid silicon latch-up effects on one hand, and on the other side, it is mandatory to be very fast in the sequencing to avoid longer booting times. BD71847 integrates all the requested sequencing and timings for all kinds of power modes and power transitions and is proven, tested and approved by NXP. A further quality attribute is the total power consumption of the PMIC. Most important is the off state as well as the SNVS or RTC state for battery-driven devices. Here, on these two graphs, you can see that the quiescent current of the PMIC is extremely low, down to approximately 18 microamp and less than 30 microamps for all input voltages and the full temperature range. The quiescent current for higher operational modes like suspend, idle, and run mode are not of that importance, as there are loads which will dominate the overall power consumptions. Anyhow, the requested power consumptions for all these modes is as less as possible to improve the thermal behavior and ensures longest operational times. Let's have a look to the PCB layout and the density. What you can see on the right-hand side is an NXP reference design. Highlighted the two main power layers. As you can see, the pinout of the BD71847 is optimized for the i.MX 8M Mini, which allow routing the power supplies easily with sufficient copper area and width to ensure low impedance routing. The area requested for the PMIC, including its externals, can be down to roughly 300 square millimeters, assuming 1 millimeter guard area for each component. Here's the answer to your question how to get access to the BD71847 product landing page. Go to the ROHM website www.rohm.com and enter BD71847 in the search field. After clicking to the magnifier, you will be directed to the product. Click onto the product and you will be automatically forwarded to the landing page. Here's the landing page. You can examine on the landing page the content of the BD71847, download the datasheet by clicking to the datasheet, or enter further technical documents by clicking onto the technical documents. Technical documents include the actual list of collateral available for free download. Datasheet, platform design guide, schematic, thermal resistance, part explanation, bill of material list, layout schematic, schematic data, evaluation kit information, Linux driver software, as well as further information on existing system on module boards are available. As a summary, BD71847 can solve the mentioned design challenges and speeds up your design. It is a fully integrated PMIC for cool, high-efficient and feature-rich designs. It is optimized for the NXP i.MX 8M Mini processor family and offers OTP technology for application optimization. The full power supply implementation with its additional features requests smallest PCB area at very low BOM cost and offers attractive value for money. BD71847 is the PMIC for the i.MX 8M Mini. Before ending the presentation, I would like to take the opportunity in mentioning two PMIC family products. First is the BD71837A, which addresses the i.MX 8M SoC family. This product is already in mass production, comes in an 8x8 QFN package, and includes two additional bugs and a further LDO. Second is a product which will be released soon and addresses the i.MX 8M Nano SoC family. This BD71850 is pin compatible to the presented PMIC, means comes in the same package, but two power supplies can be used for further platform similar to LDO4 of the BD71847.
Thank you, Michael, for the presentation. We will now start to answer the questions that have been submitted during the webinar so far. Please feel free to continue submitting your questions. Michael, here's the first question. What is the preferred connection for 4 corner pads? Is it better to connect to the ground or not?
Yeah, the 4 corner pads should be connected to the ground, which is also found in the X-pad, means in the middle part, the thermal connection of the device itself, and ensures that we have the proper and good connection and we are not running into some problems via thermals and so on, as well as the thermal issues which can occur on thermal shocks.
Okay, so here is a question from another customer whether they can be sent the presentation to them after the event.
We will send, or our Marcom department will officially put a version of this presentation into the clouds so that it can be accessed for everybody.
Okay. The next question we had is, what is the difference between the BD71847 and the BD71847A?
Okay, so the total description why we had to go to these 71847A can be found on our website in the errata for short notice. There was a minor bug found in the chip in some very seldom circumstances when the input voltage is very, very low. And during the OTP readout, there was a problem, as said, and this was corrected. Means at the end of the day, there was a metal mask update, which was necessary to fix this issue. So we are just supporting and supplying these 71847A. So the version with no A won't be submitted to the customers anymore.
Okay, and here so far as I can see, is the last question. Um, in the data sheet, it says that the bug 7 requests 22 microfarad, whereas all the other bugs will need twice 22 microfarad. Why is that?
Yeah, I said it during my presentation shortly. The bug 7 has an output capability of just 1.5 amp, means it's half of all the other bugs, and therefore it's only requested having there 1 time 22 microfarad capacitance at the output, and the bug remains stable there.
Okay, I see no more questions coming in. I guess at this point we can close our webinar. Is there anything else you would like to add, Michael?
Not from my side. Just to mention, as said at the end of the presentation, feel free to log in onto our web page, go to the landing page, and here you can find all the collaterals which are necessary, also frequently asked question documents which will be updated on a regular basis. These documents will be work in progress, so we will keep all the documents here updated and inform customers on upcoming and interesting things. That's it from my side, Sarah.
Okay. So thank you everybody for joining us today, and we will send out information with the link to the presentation shortly. Have a good day.